All right, let me check. Christopher doesn't look like he's completely signed on. Hang on. Can you hear me? Hi, Lisa. Okay, Christopher. Hey, good morning, Terry. Alrighty, so today we're going to move on to the next domain, which we've already took a big chunk of, I believe. So let's go ahead and get started. Yeah, I'm loading up now. There we go. Yep, so now we're going to finish off the communication network security. Whoops, sorry, went to the wrong one. All right. Oh, that's not what I wanted. Just wanted to. All right, gotta get my fingers good to go. Here we go. That. All right, so we have already talked about a lot of these things, but I'm just going to cover some of the key concepts, and just like how we did it in encryption, things that we've already talked about, we'll just go ahead and quickly go by. So the simplex is the one-way communication, okay, and half duplex and full duplex. We talked about this a little bit. So specifically the half duplex and full duplex. So when we did the switch, layer 2 switch, and we talked about how each of the port is a collision domain, and that if you are one workstation connected to that port, there is no collision. There's no possibility for collision because you don't have any other workstations. In that case, you can use the full bandwidth of what's provided for you on that Cat5 cable, which is you could do full duplex, which is you can send and receive at the same time. Whereas if you are afraid of collisions, you can only do one thing at a time. So you can either send or receive at the same time. So it is half duplex. Okay. And sometimes the modern network interface cards and modern switch ports will auto-negotiate and pick just the right mode so that you don't have any problems. But sometimes there is a problem with it, so that one side thinks it's half duplex and the other one thinks it's full duplex. In that case, you'll have intermittent problems. And also remember that just because you have a switch, that doesn't mean that you're always going to have one workstation connected to a port. You could have multiple computers connected to one port, maybe even like a hub, or perhaps even another switch. So you can. It's not always the case that it's always going to be. All right. So moving forward, concepts: LAN, WAN, MAN, and PAN. So local area network, wide area network, metropolitan area network, personal area network, and LAN. I've been referring to LAN as like a segment as being a broadcast domain, right? So any place where you do a broadcast, that's where it goes across. And remember, broadcasts do not go across a router. Okay. Wide area network, WAN. WANs are usually considered to be the long-haul network, so that if you, from your local area network, that you would want to go across the ocean, perhaps across the continent, then you would definitely be using a WAN. And used to be that there were totally different technologies, the MAN and WAN. So LAN, you would have Ethernet, and perhaps for WAN, you would have PPP, SDLC, 25, trim relay, ATM, MPLS, right? All these are different types, different protocols that you would use for a long haul work. But these days, now there is something called the wide area Ethernet. So even for WAN, you could start to think about using the Ethernet as well. MAN is metropolitan area network, so it's for something like a city. MAN is basically a Bluetooth network. That'll be an example of it, for now anyway. The internet, the intranet, and the extranet. So the internet, well, first of all, intranet. Okay, so intranet is the internal network. That's basically what that is. With the internet, though, hang on here. Let me see. Hey Raymond, can you hear me okay? All right now. But you, Raymond. I want to check because Raymond's connection looks a little odd. Oh, maybe not. Okay, so for the internet, right, with a big I, capital I, we're talking, of course, about the internet that we're all connected to it and come to love, the one that the ARPANET created. But also, little I, internet, is just a collection of networks connected by routers, right? So that would be the internet with a little I. Internet. Now, extranet. What? Getting to Raymond for some reason. Okay. So, what is an extranet? Are you telling me? What's an extranet? Oh, come on. Someone must know. Extranet. Anybody? Going once? Going twice? Gone. You know, I've always wondered why it's 3. Why isn't 4? Why isn't 2? And somebody told me, hey, 3 strikes and you're out. All right, so I guess maybe it's a baseball analogy. Anybody with extranet? Okay, all right, so you're going to get to see my whiteboard then. I wasn't going to do this, but since you didn't answer, all right. Okay. All right, so with the internet, let's take a look at this. Well, no, not with the internet. Let's go straight to the extranet. Extranet are networks that you share with your partners, business partners. And it's all about the security domain and the trust boundary. Take, for example, let's say that you have your partner. This is a file server. This is, partner. And here you are, working with that partner. You own file server. And that's you. And let's say that you and your partner company are doing a project together and you want to share a file, but you don't necessarily want your partner to do that because, about security, right? That would be a bad thing to do. And the same thing with the partner. They don't want you to go into that, because after all, it's security risk for them as well. So then, the idea is to share the wealth. So, oh, sorry. So, right, you share the files over there. So what that also means is that the security domains are, you have one security domain, you have, this is a security domain, and this is a security domain, right? So the highest risk right here is here. That's where you have the highest risk. Okay, but this is a logical perspective. You could actually have it something like this physically, but I'm not sure if anybody would do it. You could do this. So let's take a look at how this would look in a physical domain. Okay, so I'm going to scroll down. Let's say you have the internet in your partner company. Here. And you are here. There you are. Okay, and it's possible to create that segment. Remember the DMZ? Maybe have a device or proxy. And perhaps on this segment where we had the database before, you could have that. File server. Okay? And you could allow the person to partner to come in, perhaps, or maybe a VPN. Okay, and then to allow them access to the file server. Right. The reason why I do this is because, once again, of the security domain. So, security domain is different. This security domain and this security domain, right? You definitely do not want to put it on that segment. So you put it on the segment that's different, and you want these people to have at least some way to vet their access, so that they don't go straight into it. So you don't want them to be going, straight into something like that. It's a security risk. So that you wouldn't create a network like that. Okay, so that would be the extranet. So that would be the example of an extranet. Okay, any questions? Excuse me. No questions. All right. Okay. Raymond, can you hear me okay? You look like you're okay now. Are you good, Raymond? Raymond? Okay, good to go. All right. Okay, so that's where we're at, okay? So internet, intranet, and extranet. And remember, normally for any company, intranet has the highest security, because intranet is where you have all your internal resources, like financial servers, HR databases, right? Those are most important. Okay, so we did the OSI model, and one thing that I would like for you to look at here, right, is encapsulation. This is why I have that slide, and I did explain it. So just a review. You have the data, and of course the purpose of this whole thing, right? The OSI, it doesn't exist for itself. OSI exists so that application process 1 and application process 2 can talk to each other, exchange data. That's all that is. Okay? So as the data logically flows across horizontally, in reality it has to go down, right? Vertically down, and then go to the sideways, and then go up. In that process, each layer, as it passes each layer adds information, and they're called header and trailer information. And notice how that, how that happens at each layer. And as it goes up each layer, once the unit of information is processed, the header and trailer information is peeled off, and then it gets pushed up to the the higher layer, and then on and on and on until only the data remains, and it goes back into the application process. Okay, so that's it. So I want you to look at this one, and I want you to look at this one. Now tell me what's different. One more time. Okay, which is the OSI model. This one, which looks a little different. What's the difference? Do you notice? Anybody notice the difference? No? Is there any kind of delay in my presentation? Anybody having a hard time picking up? No? Okay. All right, that's good. So the difference here, because I waited 3 seconds inside my head, okay, is that notice how the trailer information and header information is handled here. Notice that every place except the data link layer do not have the trailer information. You see that? Right, only the header information until it gets to the bottom, and then now you have the trailer information at the data link. Okay. Now, this is wrong. This is wrong as an OSI. OSI is generic, so the OSI is supposed to look like that. You're supposed to have trailer and header information as you go down. Okay. But this is not completely wrong. It's a mistake, but I can understand what the mistake is. And the understanding of the mistake is that this person, whoever did this on the internet, has taken the TCPIP model and stuck it into the OSI. Now, if it's TCPIP, and then this is true. That is, it does not add any trailer information until you get to the very bottom, and then that's where you have the first instance of a trailer. And that'll be at the data link layer, and the trailer information is the FCS, right? Remember the CRC, which is the FCS, file check sequence. That will be the trailer information. Okay? And so I just want you to have a critical eye. Okay? And let's map this thing, right? So let's map this thing to the TCP/IP. And I don't think we quite did this last time. We discussed how OSI wanted to be an implementation, but it ended up just being a design. Okay? And TCP/IP is an implementation and was an implementation even when the OSI was being developed. That the actual thing that's working is TCP/IP. There was a work of mapping back TCP/IP to OSI, or vice versa. Okay? Now this one is the closest one that is true. This is the one that is used by your book. Your book actually has the mapping in it. It looks a little different from this, but your book's mapping is basically this. I'm going to tell you that there's another mapping to it, just so that you know. Look at it. Notice how TCP/IP only has 4 layers, right, compared to 7. Right? So what's missing? Well, the data link layer and physical layer is clumped into one. They call it the network interface layer. And notice how the application layer, presentation layer, and part of session layer is clumped into one. It's called the application services layer. The network layer is called the internet layer, and transport layer is transport layer. In your book, transport layer on the TCP/IP goes straight into the transport layer of the OSI. That is, the boundary is the same. But in reality, if you look at what it does, it actually bites right into the session layer as well. Okay, so we'll explain that a little bit. So this is a little different still from your book. Okay. But basically, for the exam, just remember transport layer goes across the transport layer. That's all. Okay, but it's not really correct. I mean, just technicality perhaps, but it's not correct. Now, isn't it curious why this thing is like this? Well, one thing is TCP/IP, I'm sure, said, look, why should I change? Right? This is how I was always. and the OSI came afterwards, so I don't really feel the necessity to change. But the thing is, TCP/IP was never a standards document design. So the division of these mapping, right, is pretty flexible. That's why there are actually several different mapping patterns onto the OSI. But the true story is much more interesting than those. True story, of course, is that when these people at the DARPA was developing TCP/IP, the only thing they cared about was the robustness of the network. That is, if the network was damaged in some way, like rocket coming in and just destroying some router groups and such, that TCP/IP was smart enough to reroute dynamically and then get the packet to the other side. That's basically what they were worried about. So the thing that requires the robustness, that does the robustness part, and to make sure that the other party is getting it, is actually the middle two layers, which is the network layer and the transport layer. So that's why, what do you think the protocol is called TCP/IP? Because that's all they really cared about, TCP and IP. And IP resides at the internet layer and TCP resides at the transport layer. That's why. Okay? That's the real story. And they said, I really don't care about what comes below and what comes on top. You worry about that. But we came out with this fantastic thing called the TCP/IP. All right? That's the true story, but it really doesn't help our case, because if you look at this thing, layer 3, which is network layer, is actually layer 2, the internet layer. That is really confusing. Okay? So there's another mapping that you'll probably see a lot, right? Not in your book though, but you'll probably see this a lot, where you have they've actually re-divided up the bottom 3. So the physical layer, the data layer, and network layer matches. So when we're talking about layer 3, we are talking about layer 3, and thanks to that, when we're talking about layer 4, we are talking about layer 4. Okay? The only thing that's missing is the session layer, presentation layer, but part of session layer is in the transport layer for the TCP/IP side. So what we're talking about then is we're completely missing the presentation layer. So what people say is that, look, in the TCP/IP, presentation layer is done in the application layer. That's how they usually talk about it. And part of the session layer is in the application layer as well. All right, so that is the mapping, and here is the review of what you call those things on each the units. On the left, OSI, everything is a PDU, right? Protocol data unit. On the right, on TCP/IP, application is called data. Transport layer is called segment. Okay, doesn't that kind of make sense though? Because remember, at transport layer, you disassemble and you assemble. So you have a big chunk of data and you divide that into pieces. Well, that could be segments, right? So these are called segments. The network layer, they're called packets once they're in that network layer. And when you go down layer, it's called the frame. And of course, in physical, it's like bits and bytes. Okay. I've used this. I kind of like this one. It is pretty depictive. It's not 100% correct, right? But a lot of things out on the internet when it comes to TCP/IP seems to be, somewhere close to the truth, whatever that is. Okay. This one obviously is a 4-layer model. So you have the network access, then you have the internet, and then you have the transport, and then you have the application, right? And let's talk about this, right? We already talked about ARP, right? Address Resolution Protocol, and we went deeply. Well, we even talked about ARP poisoning. So I'm hoping that you're okay with that. IP is what the routers speak, right? So routers are looking for the internet protocol to route. That's basically that part. And what this one's saying is that from IP then, on top of that, rise ICMP, the UDP, the TCP, and IGMP. But you have to realize, I have a note on the bottom. In CISSP, ICMP and IGMP are considered layer 3. So layer 3 as a network layer, right? So you bring those, if you can imagine just pulling those things down, right? And making ICMP and IGMP equal to at the level, with the ARP and LARP. Okay, just bring those things down, and that would be the model for the CISSP. Okay. Now, what is the truth though? Well, the truth is, it's gray. because some books will say, right in along with what CISSP says, but other books will say, well, it's kind of gray. It could be considered to be layer, 4 or not. Okay. So this is not completely wrong. Okay. But anyway, so what is an ICMP? So ICMP, when we do something like a ping, right? We're using ICMP. The ICMP, Internet Control Messaging Protocol. I just want to make sure. Sometimes it's called a management protocol, but it is Internet Control Messaging Protocol. It is used for troubleshooting the network. That's what ping is, right? It's for troubleshooting. It's a very lightweight protocol that says, hey, are you alive, right? That's ICMP echo request, and if it's alive, it's supposed to send back with ICMP echo reply. So that's a ping. Okay. UDP is what's called the connectionless protocol. Use a datagram protocol. So UDP is used to just send, to connect to the other side without actually checking if the other side is present. So it's like sending a postcard to the other person, crossing your fingers that there's going to be somebody there and somebody's going to get that postcard. But you're not really heartbroken about it if they don't get it. Okay? Because then you say, because I'm going to bombard them with my postcards a little bit later on. And I'm sure one of those will get through. Okay, it's very lightweight, isn't it? With a postcard, you don't have envelopes, you don't have, you don't write letters, big or long letters. It's just a very short message going to the other side. Okay, but it does have the drawback that you don't actually know if the other side's there and got your message. TCP it's connection oriented, so it's almost like a telephone call, right? You have to first ring the other party and make sure the other party is up and live and wants to talk to you, and you say, hey, look, I'd like to talk to you. Is it okay? And they say, yep, it's okay. And in fact, I want to talk to you too. Is that okay? And then I say, it's okay. Very, very courteous. Right? TCP, Transmission Control Protocol. Okay? And you have the IGMP, which is Internet Group Management Protocol. So this is used for multicast. How many of you ever use multicast or have set up multicast? Here. Once in a while, yeah, for mass deployments, very nice. Yeah, so Terry could probably attest that in the multicast, you have different address. So you have like a group address, and it used to be something called the M-bone. Remember, Terry, where we use the multicast backbone to send these multicast connections. And multicasts are usually used for streaming media. Something like, let's say if you're doing online TV shows, and let me see, just let's say presentation. For example, this one, right? So let's say this is a presentation, and I know that everyone is all in different location, but what if most of you are in the same location? Okay? And currently, Lincoln trying hard to create, let me see, 9 separate connections with you, so that my presentation, goes out to the world in 9 separate ways, right? 9 separate sessions, something like that. But that could be very tasking if the audience becomes, 100, 200, 300, right? I probably won't be able to handle it. I don't think Link can actually handle that much. Not sure what the limit of this thing is. But there is a bandwidth limit, okay? But that really does cramp your style, right? This is like most tools like Ghost and Windows deploy services all use it. That's right. That's right. Yeah. And the multicast then, well, what they'll do is say, okay, so how many of you are in the same location? Oh, we have 5 of you in the same location. Well, let me just send you one, connection all the way to your room, and then once it gets to your room, it spreads out into 5 different, 5 different lines. And that will be most efficient in a lot of terms. It will be efficient for me sending just one connection out instead of 5. And then it will be efficient for you guys because it just spreads out right at the end, fans out. Okay, so that's what IGMP manages. By the way, as Terry mentioned, of course, for those of you that don't know what Ghost is a Ghost. It's usually used in a training environment where we want to do massive, resetting of all the computers to the original image. So we use Norton Ghost. That is the one you're talking about, right, Terry? Yeah, so Norton Ghost to go ahead and do that. But do they still have Ghost? I could have sworn semantic discontinued. Oh, is that right? Okay, well that's good. I really like those. It's pretty simple. Um, and another one that uses the IGMP, the multicast, believe it or not, is OSPF. So OSPF, remember OSPF, right? The routing protocol, open shortest path first. So when it's looking for neighbors and talking to neighbors, they use multicast address to do that, just to be efficient. All right, and then you have the application layer programs. So BOOTP, TFTP, Simple Network Management Protocol, SNMP are all riding on top of UDP. And FTP, Telnet, HTTP, and others are riding on top of TCP. Okay, and it's why? Because we made a decision to do so. Whoever was coming up with HTTP says, I like to have a connection-oriented. I want to make sure that the other party's hearing me, so they just chose to write it on top of TCP or use TCP services. Whereas something like TFTP, Trivial File Transfer Protocol, it says, no, I don't need it. It's right there. You don't usually use TFTP as a replacement for FTP anyway. TFTPs are used usually for something like Cisco. You update, your iOS or something from the new one comes from TFTP. Doesn't have authentication at all, so you wouldn't want to use TFTP in that way anyway. So then they said, no problem, we'll just use UDP. Very simple. Okay, so these are modulations, and I hope it gives you a little bit better understanding. Now, because it's we have a ping and a traceroute, I don't believe Traceroute is that. Traceroute is an application of ping, so I think that's also not correct. Actually, I actually think that's probably the only thing that's not correct. Everything else is, gray. All right, so I'm going to show you right now the Traceroute, and I'm sure you've seen Traceroute. All right, so and I'll show you the command prompt. Let me get rid of this other one that I have. Alright, so you're seeing my command prompt. Let me adjust my window. Okay, so we'll do Traceroute. Right. Traceroute. Okay, quick start. Yeah. So what it's going to do is it's going to go look for Quick Start, www.quickstart.com. Oh, by the way, so to find out all about the IP addresses and such, you could do NSLOOKUP, right? So NSLOOKUP would be the DNS tool where you find you're talking to your DNS server, right? So if I do start.com, it's going to give me an IP address, and it's giving me that address is a 198.105.244.228. Okay, and I'm not sure if that's completely correct. Oh, you do? For what reason? What does that give you, Terry? Oh, okay. Yeah. So that's just my computer, right? Yeah. So if you do route command, route it's looking for your basically looking at your routing tables that everyone has. Oh, yeah, and of course it's not just the routers that have routing tables, right? Your computer has a routing table too. So you route. Heck, you could do route print. Whereas I think this is too big for my screen. I think that's what's happening. So you'll get routes. This is a routing table. Gives you IPv4 routing table, the interface list, right? So all these are good. I have the VirtualBox, wireless, Bluetooth, right? So I have all these things. Okay, very good. So now I'm going to do Traceroute. So but notice what's different. Notice where it says Traceroute to Quick Start 66.192.6.197. That's not what I got when I did NS lookup. Isn't that weird? Remember we got 198 something. We'll see what's going on. Ruby Shark is my my router outside going out of my home. Then, of course, it's a good thing you guys figured that I was in Hawaii, because if you haven't by today, you've seen it now, right? So you see hawaii.rr.com. And where did it go? From Hawaii, it goes to social.rr. Oh yeah, so you see how it's still in rr.com, right? It's a Roadrunner, so it's a cable network. But within the rr.com, I think it's already gone to LA, and now it's in Los Angeles. Well, it's still in LA. So it's going towards, right, Quick Start. It looks like it's in Irvine. TW Telecom. Do you know what is TW Telecom? Is that some kind of a ISP, Christopher? Oh, Time Warner. Time Warner Telecom. Oh, okay. Isn't that weird? If that's the case, then you have the 66.192.6.187. So that would be the Quick Start's www, where that points to. Yeah, I'm not sure, Christopher. I guess, right? That makes sense. Time Warner. And I was just a little confused because the rr.com, of course, Roadrunner is also part of Time Warner, I think. Oh, is that right? Oh, is that right? Right. Oh, okay, that makes sense then. Okay. And is GoDaddy in there too? Is GoDaddy in California? Do you know? Who knows, right? I'm asking. Yeah, I don't know either. So I think Quick Start actually has a GoDaddy account. In fact, it's going to California, but it's also their headquarters in California. So there you go. So what Traceroute gives you is, if you look at the very top, it says maximum. Oh, US West. Oh, okay, okay. Wow, I'm telling you, these cable companies are huge, aren't they? They control the backbone of Southern California. Okay. Wow. So there are multiple things to learn from this right now. Okay. So one, it says tracing route to Quick Start over a maximum of 30 hops. Right. Hops, as we discussed in RIP, right, Routing Information Protocol, that they are routers. So they're saying that, look, this traceroute thing, we're only going to go 30 routers, and if it's going to take you more than 30 routers, we're not going to do it. Okay. So that's 30 hops. And the reason why we have something like that is this. You could possibly have, by some quirky thing, that when you send a packet out and it goes out to go look for its home, right, the destination IP address, it may get to the point where they say, I can't find it for some reason. So it keeps on going over, routers over routers over routers over routers, just like going round and round and never finding a home. It's like a zombie, right? Well, not like a zombie. I guess it's almost like an orphan. It doesn't have a home. And if a lot of people does that, we're going to have the internet clogged with these packets that are just like going nowhere, going around, just clogging up the whole network. So we have to stop that and say, look, if you can't find a home, there's a kill switch. So if you go over a set number of hops, and if you still can't find it, we're going to kill it. Okay. So that is called the TTL. Live. Okay. Time to live. So time to live is a number that is set inside inside the header information, okay, for IP. So that is layer 3 header information. We'll talk about this, but we'll see what happens. But I just want to give you just a on this. And every time a router sees a packet, every time a packet goes over a router decrements that by 1. Right? So eventually, every time it goes over a hop, it gets -1, -1, -1. And eventually, if the TTL becomes 1 and it hits that next router, when you do it -1 on it, TTL becomes 0. When it comes 0, that's the kill switch. So the router does two things. Router will drop that packet, okay, just get rid of it, okay, and then send an error message back to the sender. Say, look, I just killed your switch. I just killed your packet, okay. And that message, it's an ICMP. It's an ICMP error message, okay. And it's that message that you've seen right here. So if you see number 1, 1 millisecond, 2 milliseconds, number 2, 10 millisecond, 10 millisecond, 11 milliseconds. These are all error messages that are coming back from the hops that we're getting. And then you may say, well, why are they giving you the error message? It's because of what I'm going to show you next. Okay, let me show you how the traceroute works. Okay, it uses the TTL. So let me go ahead and change that. Change it over to my whiteboard. Okay, so if I were to go and do this, let's say here is the destination. So this is the www dot. And let's say this is you right here. And you're doing, okay, I want to do traceroute. So you have, I'm just going to make it real simple, okay? I'm just going to make it 3 routers in between. Timeline. And the first thing you do is, with the traceroute, you're saying, okay, TTL, and you send it. That it over. Okay, at this point it will do a -1 on it. Okay, and now TTL becomes 0, so you have an ICMP error message. And then you set TTL to 2 and send it. Here it's -1, so because it's 2, it becomes 1, and then it goes forward, -1 becomes 0, and then error. And then you set TTL goes to 3, okay. Goes 1, 2, 3, and here it becomes 0, error. Okay, and you set TTL. I'll keep on going, right? And you go 1, 2, 3, 4. Now at this point, it says, hey, I hit my mark. Right, so this is like a ping. It says, oh, I got it. So now you're going to get not an error message, but you get an ICMP echo reply. Right? So everything other than, except for the last message that you get on the traceroute, is an error message coming back from the router that is in your path. Right? There are other routers, but that's the path that you just happen to take, okay, at the moment. And from that information, you could see, as you were seeing, as I was doing the traceroute for Quick Start, you saw that first it was in Hawaii, and then they went over the Pacific, and then they went to LA, and then they went to Irvine, right? And then boom, there was a server. Okay, what does this information give you? I mean, why traceroute? I mean, it's kind of fun to look at, but other than that, why traceroute? Right. Yeah. That's right. You can see the latency. So, like I said, ICMPs are normally used for troubleshooting. So if you say, "Wow, this network is really slow. Like, what's going on?" and then you notice that you're going over like 20 routers to get to someplace, or some of the router doesn't come back as fast, and say, I think there's some kind of major latency going on here. So let's flip back to that. Okay, so let me see if I can make this thing a little bit more readable. Okay, so there it is. It tells you that there were 12 routers between. Okay, and the 13th one was the server. Okay, and if you look at all the latencies, you have like number 5, 74 milliseconds. The reason why you see 3 is because usually pings will shoot off 3. So let's see. Let's take a look at it. If I were to do ping. Right, you'll probably get 3 replies back. Right, so that's, you see how, well, actually 4, huh? And notice the latency. Okay, now there's a number 10 seems to be pretty, long. It's taking a long time. And number 9, there's actually like 85 milliseconds, or number 7, 93 milliseconds. Notice that? So those are the latencies of how long it takes to come back from that point. So from here, then you say, okay, I'm not, I'm trying to guess, well, communication within Hawaii seems to be okay, but boy, once it goes to LA, it slows down a lot. Okay? So that would be troubleshooting. Now, if you were a hacker, okay, what does Traceroute give you that's going to be any use at all to you? Trying to find weakness, trying to attack, Traceroute be useful or not? Any ideas? If you were a hacker, what would this information give you? Of course, this is not the only one you'll be using, but people do, use Traceroute. No ideas? Yeah, Lisa. We'll give you IPs to attack. Well, yeah, so addressing Lisa's issues, so we'll give you IPs to attack. So when we do Traceroute, we basically know the IP for the server. We could get the IP for the server in various ways. And the IP addresses that you're seeing in between are routers. So if you want to attack any of the routers, yeah. Yeah. A view into your network routing. Yeah. So Terry, so my question was, how would that help with the attacker? It gives you an idea of what local ISPs to fish first. Yeah. So it may be if you're trying to fish, sure. And yeah, so basically it gives you, if I'm going to launch an attack, you know that my attack is going to go through these routers. Yeah, right, Terry. Yep, yep. So there you go. So remember in routing, we talked about the ASs, right? And the routing protocols that are used. But basically, if you look at this thing, and for example, like I'm sure Time Warner probably has like a bunch of ASs, but it'll give you an insight as to where the target is. So you say, it's in California. So sometimes knowing the physical location would help you in some attacks. And also, we'll talk about it a little bit later and say, I don't think I want to be going through these routers. Let's say. You say, I want to go through a different route. Then this will be a basis to, make a decision in saying, I want to go through a different route, which we'll also talk about in the router attacks. Okay. And this also has something to do with TTL. What TTL do you want to end up with when you get to your target network? Okay. And that I'll definitely need to explain once we get to the attack phase. Alrighty, so kind of keep this in mind, all right, with the Traceroute, and let's go back to the presentation material. Okay, so we talked about the ICMP. We'll talk more about TCP. Okay, so let's go. TCP ports, we talked about this, right? So we should be okay. Well-known ports and their issues, right? The privileged ports, registered ports, vendors have to register it and get it. Ephemeral ports or dynamic ports, the users get to use it, right? We get to use it. TCPIP MAC addresses, 48 bits. Mentioned that the first 24 bits are organizationally unique identifiers, so companies like 3Coms who make network interface cards get them. And the latter 24 bits are the serial numbers, so that putting it together, network interface cards has a burnt-in MAC address that's supposed to be globally unique. UI64 is another standard for the MAC addresses. The old UI stays the same on the 24 bits, but the serial number increases to 40 bits, so that gives you a lot more MAC addresses. And I guess now, because of the Internet of Things, the IoTs, that this is going to be very, very important for us to be able to have a unique physical address on things that we wear, you know, or in my case, I let my dog wear. Okay. TCP/IP, the Internet Protocols, IPv4, right? IP version 4 addresses 32 bits, right? And you do have to understand some basics of addressing. So I'm not going to go into them because these are assumed, and if you don't know them, I suggest you study them up. So as a minimum, know Class A, Class B, Class C addressing schemes, okay, and CIDR addressing. Okay, classless Internet Domain Routing addressing, CIDR. Okay. So IPv6, 128 bits. CISSP is not going to go too much into the details of IPv6. Okay. The statistics, the global adoption rate, this is just a just on the side. This is basically, you know, how well are people using IPv6, and you could be happy to know that U.S. is pretty much leading the way where we're adopting IPv6s. I just thought that was kind of neat to look at. Country, IPv6 adoption. So there it is. It's still like 12%. It's not picking up for some reason. Just on the side, why do you think people are not picking up IPv6s? Right, right, yeah. So we're talking about devices. For everybody to be able to speak IPv6, all the devices has to understand IPv6, including the routers and everything else in between. Yeah, and although the the Microsoft Windows of the world has been preparing for IPv6 for a long time now, the United States is pretty much embedded into some older technologies, IPv4, and newer ones, yeah, definitely is able to support both, but older ones are not. Yeah, so unless those things are replaced, there's not going to be 100% usage. Yeah, very good. But the issue, of course, is that, look, we've already ran out of IP addresses. Yeah, the ISPs have them, so we as a user in the United States, we don't feel the pain because we get our IP addresses from the ISPs that we connect to, and they have a whole bunch. But other countries are having major issues, right, with the IPv4 addressing because some companies, I dare say, in the United States has more IP addresses than some countries out there, and because of the Class A addresses and Class B addresses and how they were given out very early in the game, mostly to the U.S. companies. Nothing bad about it. It's just a fact. So you have the Chinas and Japans of the world that do not have it. And sure, you could use NATs and PATs, but those do not route. So that's the issue, isn't it? It was a stopgap measure, Terry. Not NATs and PATs. Sure. I mean, it's a quite nice scheme, though. Is that right? Unless you're a business customer. Yeah, yeah. But guess what? You know, once you get, that's right, you use a 10 dot network. Yeah, that's right. So let me see. But once you get IPv6 in there, you know, there's no need for that. Everybody can have an IP address, right? At least multiple IP addresses. Yeah, excuse me for my dog. Hang on. It's a trash man. Just a moment. It's gone. All right. Let me see here. Oh, let me just go ahead and look at doing the same. What, Terry? Putting everything behind the NAT and path. All computers behind NAT and paths. Is that right? Okay. Right, for security, sure. See, look at these, right? I mean, and look how they talk about it. It says a NAT device can translate a single real or public IP address to a very large number of private addresses, and we know that's not the definition, right? It's actually, they're actually talking about a path. Okay, so here there's right. So one of the promises of IPv6 is that you won't have to do a NAT, that we can all use it. But of course, the flip side is because everybody has a routable IP address with IPv6, you can be attacked directly, right, from the network. So you would get rid of that extra security layer. You have to come up with something different. So, okay, so let's just go back. I'm sure we're looking for a very interesting world out there, you know, once everybody gets an IPv6 addressing. I'm sure there's going to be some issues. And indeed, you know, the NAT and PAT, which was a stopgap measure to save IP addresses, maybe turns out to be is a good thing because of a security layer. Who knows, right, Terry? Alrighty, so we're at the top of the hour. So let us go ahead and take a 10-minute break, and once we come back, we'll continue on with this discussion.